Hello everyone, in this video we'll discuss conservation of momentum. But before that, let's have first a review of what we have discussed last time. We talked about momentum and impulse, and we learned that momentum is the measure of how difficult it would be to stop a moving object, and we learned that momentum is also equal to the product of mass and velocity. We use the symbol rho or symbol P to indicate momentum. Okay, and we also talk about impulse, which is the change in momentum. So impulse as the change in momentum can be obtained through the product of force and time. We use the symbol J for impulse, and because this is equal to the change in momentum, we can also say that J is equal to force times time, or you can also have here, because this is change in momentum, J is equal to M delta V. And knowing that impulse is actually equal to the change in momentum, we have this theorem which says that the change in momentum is equal to the impulse of that event. So here we have that again, this is J or impulse. So let's use this one. So this is J, and this is equal to the change in momentum. Okay, so we have here J is equal to delta P, and delta P is equal to mass times the change in velocity equals force times time. Okay, so I hope that you were also able to watch the guided video or the guided practice problem on Canvas and self-paced activity. So let's now proceed to the conservation of momentum. Are you familiar with this object? So some of you might say this is a pendulum. When we say pendulum, we have the bob, okay, and with the string, and this one is a bob, okay, but this is several bobs, and we can call this, this is called Newton's cradle, okay. Okay, this is an instrument used to demonstrate conservation of momentum. Okay, so we'll go back to this later. Okay, look at this. What if your science teacher will be monitoring you in the playground? I mean, the little children, of course, and doing this, of course. You should not allow this to happen. Anyway, okay. According to the law of conservation of momentum, it says that in a closed system, the momentum before an event is equal to or is the same as the momentum after that event due to constant conservation. This is according to Sir Isaac Newton, okay, from his book of Mathematical Principles of Natural Philosophy. So let's have the statement discussed or explained. So when we say in a closed system, meaning there are no other factors that would affect the motion of the object. Example, forces, outside forces, and that. So in a closed system, or no other external factors. Okay, the momentum before the event. So we have this event. What event is this? So here we are pertaining to what we call collision. Okay, collision of object when they hit one another. For example, a ball, two objects moving towards each other and they hit each other, and so the momentum of this object before the collision is the same as the momentum after the collision. Okay, mathematically written as momentum initial is equal to the final momentum. Okay, so we can have here initial or before the collision, and then after. So you can see this apostrophe as prime. Okay, you can read this as prime, which means collision happened, or this is already the final momentum after that event or that collision. Okay, now let's talk about types of collision. Basically, we have two types of collision, which is elastic and inelastic. Okay, we have elastic and inelastic collision. But under inelastic collision, we still have two types, which is perfect inelastic and imperfect inelastic collision. So let's see. These are the illustration and see what happens. So you can describe the two types of collision. Let's have first inelastic collision. So for inelastic collision, again, we have two, imperfect and perfect inelastic collision. So as you can see here in the illustration, before the event or before the collision, they will be moving towards each other, or either one object will be moving towards another so that it will hit the other object, and then see what happens after the collision. For imperfect inelastic collision, objects do not stick together. Okay, so after the collision, they will be moving apart from each other, either in opposite direction or in the same direction, but again, they will not stick together. While for perfect inelastic collision, okay, so here you have 0% of elasticity. So the object, after hitting each other, will stick together and will result to same momentum. Okay, or I mean same velocity. Okay, because they will be moving as one. Okay, so both type of inelastic collision conserve momentum. Okay, so but not the kinetic energy. So one may stop, or the other one will continue to move. Okay, but again, this shows conservation of momentum. Well, for elastic collision, so as you can see, objects will not stick together again. So it's similar to imperfect inelastic collision. So you can observe this in a microscopic world. Okay, so can be observed in fundamental particles, particles in the surrounding. But similarly, what happens to billiard balls? Okay, so this cube ball will hit the other balls, and it will transfer its kinetic energy to all the objects, and these objects that are at rest will start to move, and they gain their momentum. Okay, so but basically the idea is this type of collision, objects will still not stick together. Okay, they will have their individual momentum. So let's have the equation for elastic and inelastic. So again, for inelastic collision, we're pertaining here, we are talking about here imperfect inelastic collision. Imperfect. Okay. Because elastic and imperfect inelastic collision will have the same illustration or the same concept, that objects will not be moving together. So, knowing that this object, okay, before moving has its own momentum, we name this as P1, the momentum of the first object. And the second object will have its momentum as well. So, this is P2. Okay. After collision, of after colliding, so they will have, of course, change in velocity. The velocity will change. Example, this is moving faster because it hit another object. It might move a little slower, or it might stop, or again, they will have different velocity. So we will name its velocity as P1 prime, indicating that this is already after the collision. And the other one will be P2 prime. Okay, so going back to the law of conservation of momentum, according to that, we have here, and P before the collision, or the momentum before the collision, is equal to the momentum after the collision. So we will have here, this is the momentum before the collision, so that's P1 plus P2. And on the other side, we have here P1 prime plus P2 prime. Alright? So, knowing that momentum is equal to mass times the velocity, So let's have it here. So the momentum of the first object will of course be m1 v1, mass times velocity. This is the first object, so we indicate sub 1, or we use subscript to indicate that this is for the first object. And for the second object, we have the momentum of the second object, that will be m2 multiplied by b2, okay, equal to p1 prime. So again, here is only the velocity of the object that will change. So we will have here m1 v1 prime. So this means that the object has its new velocity after the collision, plus the second object m2 v2 prime. Again, prime indicates that this is after the collision. So here, this is your equation for elastic collision and imperfect inelastic collision. So, in dealing with problems, most of the time you will be asked for the velocity, the final velocity of one object. So, using this equation, you have to know how to derive that. Okay? So, let's have the second one. For perfectly inelastic collision or perfect inelastic collision, so we have here, okay, so again, this object will be moving towards the other object. It will have its P1, okay, and the other object has its momentum as well, that's P2. And then after the collision, because we know that perfectly inelastic collision, in perfectly inelastic collision, object will be moving together, okay, so they will stick, so they will have new momentum. It's neither P1 or P2, but it's P prime. So here we'll have here, okay, P1 plus P2 equal to P prime, because this is now object that is sticking together, okay, so combined. So let's have here the momentum of the first object, again, that is m1 v1, and for the second object we have m2 v2. So this is now equal to p prime, or the momentum of this object. As you can see, they will stick together, so the mass will be combined. So we'll have here m1 plus m2, and they will be moving at one velocity, so we'll just have a v prime. Okay, so for perfectly inelastic collision, this is your equation. Okay, so take note of the equation. So I have here another slide. So yeah, the equation of conservation of momentum. Again, we'll have same equation for elastic and imperfect inelastic collision. And then a different equation for perfect inelastic collision. Okay, so in solving problems, you have to analyze first, or to identify first, the type of collision, so that you will know which equation are you going to use. Okay, and the guided practice problem is already uploaded on Canvas. The video of the lecture, that, so you may see that. Okay, but then we'll try to solve other problems. Let's see. Okay, in this problem, after a hold-up, Robin Banks flees in his 1,575 kilogram getaway car at 20 meters per second. He crashes into a 45 kilogram highway barrel, which is at rest. If Robin Banks' car moves at 18.9 meters per second after the collision, how fast does the barrel move after being hit, assuming that it is thrown away? Okay, so if you wanna illustrate this, you may illustrate that. Again, it's not required, but it's good that you may illustrate this one. Okay, so let's first try to identify the type of collision, assuming that it is thrown away. So after hitting the barrel, okay, by the car, it is thrown away, so they will not stick together. So this is elastic collision. Okay, so let's identify the given. So for our given, it's important that you label it correctly. Okay, so we set the first object is the car, so we'll have M1 and then V1, and let's just indicate. So the mass of the object is 1,575 kilogram, and its velocity, initial velocity, is 20 meter per second. After the collision, this now moves. Let's have here. It moves 18.9 meter per second. So that is after the collision. So we have that as V1 prime equal to 18.9 meter per second. And the second object will be, of course, will have the subscript 2. Its mass is 45 kilogram. It's actually heavy. Okay. And it is at rest, so its velocity is 0 meter per second, right? And you are asked to find how fast the barrel moves after being hit. So that will be your V2 prime. Okay, so from your equation, so let's write the equation. M1 V1 plus M2 V2 equal to M1 V1 prime plus M2 V2 prime. So we are asked to find V2. So let's derive the equation. So we will have here, let's just arrange, or I mean, like organize our equation. M2 V2 prime equal to, we'll have here M1 V1 plus M2 V2 minus M1 V1 prime, right? So that is prime. So divide both sides by M so that you will be left with V2 prime. So M2 over M2. Okay, cancel out this one. And now you have this equation. So this is our equation, and let's now substitute the values. So here and now, let's try to compute this, and the answer will be 38.5 meter per second. Okay, so that's it. Let's have a second example. A 1,950 kilogram car going 12.5 meter per second rear ends a 1,500 kilogram sedan moving at 3.0 meter per second. After the collision, the two cars move together as one unit. What is their final velocity? Okay, so this gives us the clue of what type of collision we're dealing with. So this is perfectly inelastic collision. So let's identify the given. So let's try to write here on top. So this will be our M1, okay, and this is our V1, right? And this is our M2, and then this is V2, okay. But of course, you may write it here. Okay, I just write it this way so that we can have the equation here. So because this is perfectly inelastic collision, again we'll have here M1. Our equation will be M1 V1 plus M2 V2 equal to M1 plus M2 multiplied by V prime. And we are asked to find the final velocity. So we'll divide both sides by M1, oops, plus M2. M1 plus M2. So our equation will be V prime is equal to M1 V1 plus M2 V2 all over M1 plus M2. Okay, just substitute the values. And now let's try to solve this on our calculator. So we'll have here V prime. So let me write it here. Oops. B prime, B prime is now equal to 7.50 meter per second. Okay, so again, the first example is elastic collision, and this one is perfectly in elastic collision. You may also see other problem solving on Canvas. Okay, if you have other questions, you may send me a message through Teams. Okay, thank you.